I'm just filling a cup with some liquid nitrogen. Put that liquid nitrogen right there. Might have to get some more in a little bit. Get my superconductors ready to roll. Got a superconducting disc right here. Place that right there, baby. Okay, let's fill this cup here with a little bit of liquid nitrogen. Oh, that's beautiful. Come on, baby. That's beautiful. Okay, in goes our superconductor. Oh, it looks like my cup might not be big enough for it. Let's see if we can get that baby cooled. Let's see if we can get that chilled in here. There we go. There we go. That'll take a little bit. Let's top it off here. And we're going to be able to notice pretty soon if that's going to be superconducting or not. All right, I think I'm ready. Let's pull that thing out. I think it might be chilled to below its critical temperature. We're going to find out. All right, out it comes. Place it right there. Let's get a little magnet on here and see what we see. I think it's working. Oh, let's try it here. There we go. There we go, baby. Come on now. Come on now. Look at that. Look at that. It is hovering above the magnet. Yes, indeed. The magnetic field from the magnet is interacting with the superconductor, and that's allowing that superconductor to float on top of the magnet. Isn't that cool? I can even pick it up. Watch this. Oh, here, we'll try it like this. Look at that, man. Thank you there, Salmitos. How you doing there, Ashreeve? Isn't that cool? Is it recorded? Yeah, I think there will be parts of this that that I can show are recorded. Now, as the superconductor warms, the smoke is from the liquid nitrogen that is interacting with water vapor in the air. So that's what that's from. You can see this. Look at that. Oh, it's going out of screen, back in screen. And as the superconductor warms, it'll get above its critical temperature. And then this effect you can see here is no longer working. So when that happens, we got to chill it back down again. So let's do that. Take my, whoop, spilled a little bit. A little tough to see in the dark here. Let's pop it back in. Come on, man. Just pop it in there. There we go. Pop it in there. Top it off. A little bit of liquid nitrogen. Get that superconductor good and cold. Thank you there, Salmitos. Appreciate that. I think it might be ready. I don't know. Give you a look down in there. Isn't that cool? You can kind of see the the little bits of nitrogen as they're popping into the air, interacting with water vapor in the air and forming those trails of smoke. That's really beautiful. Really beautiful. Okay, I think we're cold enough. We're going to take this baby out. Let's stick it on our magnetic plate this time. Ooh, got a little bite there. That happens from time to time. All right, there that is. We're going to place my superconducting circular magnet. What's interesting about this, well, just, hey, thank you. Look at that. Somebody just sent me a gift. Appreciate that. Can I explain why it happens? I can. Now, this is going to be a little bit tricky here. This superconductor here is what's known as a type 2 superconductor. Now, superconductors expel magnetic fields. And this is a special superconductor. It's known as a type 2 superconductor. So type 2 superconductors have impurities embedded in them. So you can think of the superconductor as a wafer. Here, I'll back it off so you can kind of see what I'm talking about. It's like a wafer, okay? And the magnetic field is coming out of, this circular system of magnets here. And that field actually penetrates the impurities, okay? So it usually goes around a superconductor. It can't penetrate it. But the type 2 superconductor, that has impurities in it through which the magnetic field can penetrate. Now, what's interesting about this particular system of magnets is the way the physics works is the field can only penetrate the superconductor at a single point. And that's why this superconductor is rotating. It's only pinned, so to speak, at a single point. And that allows that superconductor to rotate. If we use a different set of magnets like this one, this is a more constant magnetic field all across this system here. This will penetrate the superconductor at a variety of points, and this one's not going to rotate. It locks it in place. It locks it in place, man. I see you there, Krishma. So yeah, so whatever orientation I place the superconductor in, it's going to stay in that orientation. Isn't that wild? It's just absolutely gorgeous. Oop. Boy, that almost hurt. Oh, there we go. I got all these magnets here. They're extremely strong. I got to be careful with what's going on. Isn't that it's just so beautiful. Look at that. Look at the flow pattern coming off of this. Oh, it's just gorgeous. Hello there, Woody. Thank you there, Krishna. That's right, Salmitos. It has to be cooled below what is known as the critical temperature of the superconductor. So the critical temperature of this particular superconductor happens to be 93 Kelvin. And as it warms, it'll lose its ability to repel the magnetic field. And the interaction with the magnet is going to change. But I can tell it's below 93 Kelvin right now. Liquid nitrogen is 77 Kelvin. You can see it's not quite interacting as well as it warms. It's got a little, the superconductor is protected by that black disc. And you can see I've dropped the superconductor a few times, which is why the black disc is cracked. But yeah, it's warmed pretty much above its critical temperature now. So we're gonna have to drop this in some liquid nitrogen if we wanna get back to business. So let's do that. Thank you there, Woody. I appreciate that. Thank you there, Kirishima. Thank you. It was floating. Here we go. We got to get this guy chilled back below. Now this stuff, liquid nitrogen, that's 77 Kelvin. We got to chill the superconductor to below 93 Kelvin, so the liquid nitrogen should certainly take care of business for us. I'm going to leave it in there. We're going to reverse cook it for a while so we can go ahead and get it down to below its critical temperature again. All right. I'm getting a little more liquid nitrogen so I can get this baby chilled, and we'll get back to business. We'll get back to business. Oh, I love that there, Juan. Thank you. What is the actual composition of the impurities? What a great question. I love it when somebody asks me a question that I actually don't know. So I can tell you what the superconductor is made of, but Mitos has given me some homework. The superconductor itself is made of yttrium, barium, copper, and oxygen, but I do not know what the impurities are. So thank you, Salmitas, for giving me something to learn. By the way, if anyone will go ahead and look that up, what are the impurities in a YBCO? So you're going to want to look up what are the impurities in a YBCO superconductor. So once again, if somebody can look that up for me, you're going to be able to teach me some chemistry. I love it when people teach me chemistry that I don't know. So what are the impurities in to be specific, a type 2 YBCO superconductor? The superconductor itself is made of yttrium, barium, copper, and oxygen. So we're going to go ahead and pop this on. Let's do this magnet here, okay? I'm going to pop it on this one here. I got to pay attention here. All right, so, yep. Get that on. And let her rip, man. Let her rip. So the way the physics works, the superconductor, superconductor is pinned on a single point in this system of magnets. So the impurities are penetrating the superconductor in a way that makes it so the field can only pass through the superconductor at a single point. If superconductor is rotating above magnet, there should be a flux change through it, then shouldn't be current in it. So I believe, Ashirav, that the flux through the superconductor has to remain consistent. The flux through the superconductor has to remain consistent. There you go, man. Absolutely beautiful. What's meant by flux? So it's the rate at which the magnetic field penetrates these things they call flux tubes. So the impurities are flux tubes. So the magnetic field goes through those flux tubes, and it's going to flow through that at a certain rate, and that rate's got to stay constant. If you try to change that rate, the superconductor is going to be upset, so to speak. Yeah. We'll stick it back. You know, let's play around with these magnets. All right, it's kind of fun to do that. Let me get this off here. I have to pay attention though. These magnets are really strong. I can pinch my fingers. All right, let me just chill this down just a bit first. Let's get it chilled. Get that in there. Woo, that's cold. All right, fill it up so I make sure I get this good and cold. Come on, somebody look it up for me. What are the impurities in a YBCO type 2 superconductor? Someone out there is going to teach me some chemistry today, I'm hoping. Come on, man. You're going to win the comments if you answer it for me. What are the impurities in a YBCO superconductor? Type 2. Is liquid helium the fastest substance? I'm not sure what you mean by fastest. Do the molecules in liquid helium move the quickest? I would say no. Gas molecules at room temperature, for example, move, the molecules move like as fast as a speeding bullet. All right, we're going to pop that there. There's my superconductor all chilled down and ready to roll, baby. And now we're going to take this magnet, we're going to stick it on top, we're going to see what happens. Come on now. Come on, people want to see something cool. There it is. There it is, man. We got it rotating. There it goes. Beautiful, huh? Absolutely beautiful. Whoop, fell off. Try that. Pick it up. The interaction is going to be working until, I think my superconductor is warming above its critical temperature. We got to get this thing cold again. So we're going to bring in the liquid nitrogen. Pop it back in. Pop it back in. Let it chill down. There's a look down into the liquid nitrogen. I probably should have used a slightly larger cup. There it is. Cell Midas. Green phase. Yttrium, barium, copper oxide, nano oxides. Looks like barium zirconium oxide or barium tin oxide. Oxygen, awesome. So I'm guessing, so what I'm seeing is it's going to be zirconium and tin. Because, you know, the barium's already there, the oxygen's already there. So it looks like they dope it, so to speak. That's what they usually call some impurities. They call them dopants. So it looks like zirconium and tin. I will be checking on that after the live, but I'm going to tell you that Sal Mitos not only asked the question, but also found the answer, and I love it. Thank you so much. Could be. Could also be sodium ions. We're going to check those out. So what are the vapors? The vapors are, this liquid is extremely cold, and it's vaporizing. You can see as I put as I put my tongs in there, it starts to boil more quickly. And so I know this sounds funny, but this liquid is very cold and it boils. Because it's so cold, it boils at like negative 321 Fahrenheit. If you do Celsius, it's negative 196 Celsius. So even the vapor that comes off is extremely cold. Now you can't see the vapor from the liquid nitrogen, the gaseous nitrogen, you don't see that. But what you see is as that nitrogen boils off, the cold nitrogen gas condenses water vapor that's in the air. So you're looking at condensed water vapor, which is actually little tiny liquid droplets. That's what you're seeing. So when you see the steam, it's not really steam. Steam is gaseous water. But the quote-unquote steam that you're seeing, we're going to call it steam, it's more like a smoke. That is little tiny liquid droplets of water. Come on, man. I'm trying to rotate it so I can get the whole thing. There we go. That's what I wanted. That's what I wanted. Tiny particles containing zirconium are added to awesome. Awesome. Looks like it's zirconium. Zirconium and tin, baby. Haha, love it. That's awesome. All right, here we go. Gonna move this aside. All right, let's get this on top and get her rotating. Come on now, pin in place. Pin in place and rotate for me. There it is. We've got our superconductor levitating in a magnetic field and rotating away. Isn't that beautiful? Absolutely. Now, I notice that the superconductor is starting to sort of lose its ability quite quickly. That tends to happen. So what happens to these things? The crystal, the superconducting crystal, is, a lot of water ends up crystallizing in it. Water from the atmosphere seeps in there. And when that water in the atmosphere seeps into the crystal, the superconductor ends up losing its superconducting ability, even when chilled. Get that going, man. How's it levitate? Here's the way it levitates. The way it levitates is superconductor expels magnetic fields. And this is a magnet. And so if I were to push this all the way down onto the superconductor, what would happen is the magnetic field would have to penetrate the superconductor. So because of that, it's very difficult to get the superconductor and the magnet to touch. And so there's sort of a repulsion force that sort of pushes up on the superconductor when you try to press it down onto it. Now, it's losing its ability to superconduct right now because it's being warmed above its critical temperature. Well, folks, that's all I'm going to do for today. I enjoyed doing some, that'd be cool, Salmitos. I had a good time hanging out with you today. Thanks for joining in. I do these every once in a while. Leave a like on the channel. Maybe consider subscribing. It's great having you guys on board. I do these once or twice a week. So, good. Thank you there, Salmitos. Thanks for teaching me something, and we're going to see you guys next time. All right. So long, folks.